T, man, what are you guys doing? Join. Don't connect. Don't connect. Meeting ID. All right. Let me get rid of this. Okay, let me hit done. Let me share. Where is it? Share my screen. Start the broadcast. Okay. All right. All right. Stay as a participant. Okay, we're back. All right. So I guess let me see. I'll keep a log of who's coming and going. As long as you're in one of these sessions, you're good. Okay, so this is part 2. We're just going to kind of keep going. Hopefully, we'll just kind of go as far as we can. So as x goes off to the far right, the function tends to 200. As x tends to the far left, it tends to 0. Let's see how do we do. So we got 2 horizontal asymptotes, y equals 200 and y equals 0. Let's see. So as x goes off to the far right, we get to 200. So the line y equals 200 is a horizontal asymptote of this function. As x goes to negative infinity, it tends to 0. So the line y equals 0 is also a horizontal asymptote. Do they have the image? And here's the image, all right? So we get something like this. So again, we just kind of evaluated this as x goes off to either positive infinity or negative infinity. The takeaway is, the trick here is being able to identify those terms that tend to 0. Like the first one, that 25 e to the negative 2x, that specific term tend to 0, and it left us with 200. But the second option, the whole denominator went to infinity, so we had a fixed number of infinity, which is essentially 0. So that was an interesting example. Okay, I'm gonna do a quick scan. Oh man, I would love to do one. We are totally out of time because we really do need to be going to the next section. I'm gonna attempt to do one. I'm going to kind of read through this. This is on the strategy for sketching graphs. So I have a procedure when I'm sketching graphs. It's about 6 steps. First, I explore my intercepts. I'm gonna let you read through this. Let me see, because it's a lot. It kind of goes. But I use a first derivative and second derivative. Okay, I'm going to summarize this myself. I'm going to let you read through this on your own. Okay, I'm just going to do my own summary. So when I'm sketching a curve, things that I like to look at. So first thing I like to explore are my intercepts. My intercepts, right? And usually I like to start with my y-intercept first. Oftentimes that's easier than the x-intercept. Then I'll explore my x-intercept. For rational functions, the x-intercept is when the numerator is 0. So then the next one, I like to explore my asymptotes. Okay. So then I usually like to start with my vertical asymptote, right? See if I can find anything there. And then after vertical, I might try either the horizontal asymptote or the slant or oblique asymptote. Right? So those kind of go together. So then, okay, so then we might do some tests. Let me see. We could do a test for symmetry. Let me see. So then the third, we might do our first derivative test. That's first derivative test. So that's increasing, decreasing, or constant. That's our relative max and min. We might do our second derivative test. So that's going to tell us the concavity, like concave up, concave down. I'm going to throw in there a test for symmetry. I think that's from college algebra. If you do that, you don't have to do that if you're not feeling it. And then a few additional points. So I'll abbreviate it as few additional points between and beyond your vertical asymptotes and x-intercepts. Hey Google, stop. So a few additional points between and beyond your vertical asymptotes and x-intercepts, right? I'll just abbreviate them. See, between and beyond the vertical asymptotes and x-intercepts, right? So a few additional points there. And then lastly, you just put it all together as best as you can. And then lastly, you graph. So, you know, when I'm curve sketching, these are this is like a summary of everything. So then I go back and I explore each individual part and try to put it together. I totally want to attempt this. Like we really should go into the next section, but it eats up a lot of time. Okay. So let me duplicate this. Duplicate. I want to clear page. Okay. And I'm gonna just screenshot this and use it as a reference. And so again, like when you look at it in its totality, it's daunting, but each individual part within and of itself is actually not too terribly bad. You just got to slow down and take it part by part. Don't try to do all of it at once. You know, my dad used to have this quote, "How do you eat an elephant?" I'm like, what do you mean, how do you eat an elephant? I was like, I don't know how. And he'll say, one bite at a time. All right. You're not going to eat the whole elephant. You eat it one bite at a time. So I'm going to, anyway, so that's the idea. All right. So I'm going to use it as a reference and let's just do part by part. Okay. Let's see what happens. So first, let's look at our intercepts. Whatever. I don't feel like writing right now. You know, this is intercepts. So I like to start off with the y-intercept. Okay, so for the y-intercept, what do we do? Set x to 0. So if we set x equal to 0, looks like we get what, a -2. Right, crosses the y-axis at -2. So again, oftentimes the y-intercept is easier than the x-intercept, so that's why I like to start with it. Okay, so we did a y-intercept. So then if we can do the y-intercept, then it stands to reason. Let's go ahead and explore the x-intercept. So for the x-intercept, that's going to occur when what, y is equal to 0. And for a rational function, that's when the numerator is equal to 0, right? So this numerator will never be 0, so there's no x-intercept. So we got no x-intercept there. Okay, so those are our intercepts. So if setting the numerator to 0 gives us the x-intercept, then setting the denominator to 0, what is that going to give us, right? So then our second installment, that leads us into our asymptotes. I may or may not be saying that right, but I'm just going to go with it. So again, we're going to start with the vertical asymptote. And that's going to occur when what? The denominator is equal to 0. You see how in the previous we explored the numerator to 0? Now we're going to see, well, what value of x makes the denominator 0? And from here, it looks like it's plus or minus 2, right? So the vertical asymptote is going to be x equals plus or minus 2. So we do have two vertical asymptotes, right? Next, let's explore. So if we could talk about vertical asymptotes, we can also talk about horizontal asymptotes, right? So I think I'm partial to the way we do it in college algebra. We compare the degree of the numerator to the degree of the denominator. The degree of the numerator is less than the degree of the denominator, so that's going to be case number 1, which means that y equals 0 is a horizontal asymptote, right? Okay, if we factored out x squared from all terms, and we take as x goes off to positive infinity, we're going to get like we're going to get 0 over some number, which is 0 in that case. So the horizontal asymptote is going to be y equals 0. So we got a horizontal asymptote. Okay. Our test. We need to do these derivative tests. They're a little bit pain because it's a quotient, but we need to do it. So first derivative and second derivative. I guess I'll do this over here. I don't know if there's enough space. I'll start here. 3. I'll call it derivative test. Okay. And we'll start off with the first derivative test. And I'll kind of work over here on the side. Okay. So then let's go ahead and find f prime. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay. Okay. Any critical number. So the critical values are going to occur when x is either any x that makes the first derivative either 0 or undefined. So from the top of this guy, x equals 0. From the bottom, plus or minus 2. So our critical numbers are 0 and plus or minus 2. Okay. I kind of want to go ahead and find the second derivative as well, which I really don't feel like doing. Let me try this. Hang on. Give me a moment. Let me do these critical values first, because that second derivative is looking like it's getting nasty. So say this is my positive x in this direction. Our critical values we got what, a 0 and plus or minus 2. Okay. So we want to explore these guys in the first derivative. Now at -2, I think that's our vertical asymptote, like we said earlier. So I'm going to label it like this, vertical asymptote. And I'll do this color, so we know that that's something else. Same thing over here. I'll just duplicate this. So we already know that those are vertical asymptotes. And then when x is 0, that makes the first derivative 0. Okay. So then these critical values, what they do, they break the number line up into like into 4 regions that we're going to test. Just trying to generate a little bit of space. All right, 4 different regions. So here's like region A, region B, region C, and region D, right? So now we can test in each of those regions to get the sign, or we could also look in at the second derivative. I feel like I need to go ahead and find the second derivative. I'm kind of avoiding it, but I need to go ahead and do it. So I'll just kind of go ahead and start it here. Second derivative. All right. So the bottom times the derivative of the top. I think I might skip it. I just don't feel like doing it. We can do it, and we'll come back to it. Let me think. Bottom times the derivative of the top minus the top times the derivative of the bottom. That's going to be a lot that I just don't feel like doing. I need to do it on the next slide. I'm going to attempt it. It's eating into our time, but I'm going to attempt it on the next slide. Let me see real quick. The bottom, which is this guy. Derivative of the top. Bottom times the top. What is that, a -16? So the bottom times the top minus the top. So double negative is positive. Times the derivative of the bottom. It's the 2. You got this x squared minus 4. That's now a 1 times 2x all over the bottom squared. Quantity to the power of 4. Okay, so that's the second derivative. Let me think if I can clean this up. We could factor out an x squared minus 4, right? So if we do that, this is gone. This turns into a 1. This turns into a 3. What else? Is anything else cancel? Okay, that's gone. We can combine those. Looks like we can factor out a 16. Okay, let me factor out. Let me think. Give me a moment. I think I'm going to factor out a 16. So if we factor out 16, what's left? We're going to have 4 minus x squared, because we got to account for that negative. That's factored. 4x squared. So then plus 4x squared over x squared minus 4 cubed. Okay. So that's a 3x squared. I'm just going to change it here. So this now becomes a 3x squared plus 3x squared. Okay. And honestly, this is fine like that. That should be good. Hopefully that's correct. Okay. So now again, going back to the first derivative, we can test those different regions and get the sign change, right? Let's see what happens real quick. If we put the -2 into the second derivative, and the numerator is going to be positive. I think that's going to make a 0 there, so we don't get a result there. All right, so let me default back to my first derivative. So for instance, let's choose when x is -3 into the first derivative. -3 into the first derivative, the numerator is negative, denominator is positive. It looks like this is ultimately negative in this region. Let's try -1 into the first derivative. That's positive. That's positive. So it looks like it's positive. The first derivative is positive in this region. We got a negative here. Let's keep going. We're almost there. In region C, let's use +1. If we plug +1 into the first derivative, we get a negative on top. We get a positive on bottom. So ultimately, this guy is negative. And if we choose something like 3 into the first derivative, we get a negative on top, positive on bottom. It looks like it's a double negative. Am I doing that right? Let me see. If that's a 1, that's negative. That's positive. That's negative. If that's a 3, let me check over here. I think something's off. Double negative, that's positive. That's positive. So this is positive. So I think that first one was off right here. I'll do it in purple, or I'll do it in a different color so you know the mistake. I think this is supposed to be a positive there. And then I think this is a negative here, right? If we do 3, that's negative on top, positive on bottom. So that's ultimately negative, right? So based on the first derivative test, what this is telling us, the only time when we get a sign change in the first derivative is basically when x is 0, right? So that means if it's going from increasing to decreasing, that means that's a relative max. So we have a relative max there. That's the only relative max. Point of concavity would occur where the second derivative is either 0 or undefined. Let me see, the 0 for the numerator. Let me see. Okay, I need some space. 4 plus 3x squared, subtract, it's going to be a -4 square root. You're not going to have one, right? It's a U-shaped graph. You stretch it vertically, you move it up by 4, you stretch it vertically. So there's no x that's going to make the numerator 0. What about the denominator there? If we do plus or minus 2, looks like it makes a 0 there. So then our critical values for the second derivative, our candidates would be plus or minus 2. We would have to do the test like we did. Like if we choose -3 into the second derivative, that's going to be positive. That's going to be positive. We're going to get a positive. Okay, I'm going to do second derivative in green. I'm just going to put it like here. I know I'm out of space. You have to forgive me. But the second derivative, we get a positive on the left. Like in between the two, something like I'm going to choose 0 for in between. That's positive. That's negative. We get a negative here. So in between -2 and 2, we get a negative second derivative. So that's concave down. I'm anticipating a positive on the right-hand side of 2. So then, like, if we choose like 3, that's positive. That's positive, right? So what that means is that plus or minus 2 are our points of inflection. I know it's a little jam, right? But we got our points of inflection there, all right? So we have our relative max when x is 0. We have points of inflection at when x is plus or minus 2. Okay, we're going to do our best to put all this together. I'm going to bypass the test for symmetry right now, just for the sake of time. I'm going to bypass a few additional points. Let me see, x-intercepts. We have enough to put it together, right? Let's kind of go with this. Okay, so let's do our best to put this together. Let me think. I'm going to duplicate this. I'm going to clear this page. Okay. And I think I'm going to leave my little thing on the side here as my reference. Okay, so we got plus or minus 2. Again, I should do a few additional points, but I'm just going to kind of go with it. I'm going to do a rough sketch because I am kind of like in a little bit of a hurry. All right. Nope. So we're going to let this be our positive x. This is going to be our positive y, okay? Now our x values, we got, it looks like it's a lot of 2s. So I'll go to maybe like 4 on the x-axis on either side. So I'll go like 1, 1, 2, 3, 4, 1, 2, 3, 4. Okay. The y's, let's see. We should, this is where the additional points would come into play. We'd have a better sense of those y values. Let me see. 5, let's do 3, 9 minus 4. I'll go, I'm thinking like 5. I'll go up to like 10. I'll go up to 10 in either direction. Let's see, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Again, this is the origin. We went 1, 2, 3, 4, 2, 3, 4. These guys are negative. We went 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. These guys are negative. Okay. All right. So let's start off with our y-intercept. We got a y-intercept of 0, -2. So I'll put that right here. I said that's the point 0, -2 for the y-intercept. I think we had no x-intercept. Okay. We had 2 vertical asymptotes at ±2, so I'm going to capture those. So we got one here. All right. I know it's a little bit, this thing, but this is our challenge, right? That's decent. And then let me duplicate this. Okay. So again, this is x equals 2, x equals -2. So we got our vertical asymptotes. Let's see. Horizontal, we had the x-axis. So we had that this was a horizontal asymptote. Style. Okay. And that's going to be y equals 0 for the horizontal. Okay. Let's see. Now we had a relative max at when x was 0, right? So this is a relative max. I'll label it like this. We're going to say this is a relative max here. Okay. And points of inflection. Okay, so we did have points of inflection at ±2. So that just means that the concavity changed. It went from concave up to down to up. Okay, so it wasn't really a point of inflection, but the inflection did change. And so when we put all this together, again, if we chose a few additional points between and beyond the x-intercepts, it'll be a little bit easier. But essentially, we're going to get an image like the following. So like here, we'd have something here. It starts close, finishes close. So all I'm doing, like on the far left, I'm starting close to the asymptote. If we choose a few additional points, we can plot them, and then I finish close to the asymptote. In the center, again, I'm going to start close, pass through a point, and then finish close. Something essentially like that. Again, a few additional points will help this. Just in the sake of time, I'm just trying to pull it together. Right. So once we did those features that we did in the previous slide, we just come back and look again. Let's choose a few additional x values. Like I would choose like at least just one in this region. I would choose one here. I would choose one here, and I would choose one here. So if we choose x values in those regions, we can just choose the x, find the corresponding y. But if you put it all together, you should get an image like this, right? So, So let's recap that real quick. I know that ate up a lot of our time. We only got about a solid 15 minutes, so we'll do the best that we can. We did our intercepts. So I'm going to assume that it's correct. And I want to kind of see the way the textbook did it, right? So let's look at what they did. Sketch the graph. First, they started with the intercepts. They started with the y-intercept like we did. So 0, -2. No x-intercept. Vertical asymptote ±2. Y equals 0 was the horizontal. So we got those. Slant. There was no slant, right? We did have a horizontal. Yeah, they got the horizontal. Okay. Then they used the first derivative and second derivative. I think we got both of these. It was a little bit extra, but that's the nature of the beast. So that's our charge. Critical values from the first derivative plus or minus 2. There's only one, right? Which is x equals 0. I think that's exactly what we got. And yada yada yada. 6 of 10. Keep going. Yada yada yada. Inflection point. But it went from concave up to concave down, right? Which we captured. We got the concavity. We got all that. And we got the exact same image, right? So, and see, and they actually have the few additional points as well. That's what this table on the left is. So again, we explore the intercepts, asymptotes. We explore the first derivative, second derivative, and then once you've drawn out all the information that you can, a few additional points, and you put it together. Easy peasy, right? Psych. Say psych. Say psych, right? I'm sorry. I'm definitely borrowing from this content creator on YouTube. His name is Skizzle. And he's always like doing like random videos. As of late, it's been a lot of like UFO stuff and like Trump and GTA 6. He just in love with GTA 6. That's what he always talks about. So funny. But like when the crazy things happen, you like, say psych. Oh man. Oh my God. Please say psych right now. So, I mean, but again, I feel like the takeaway here is in totality, it's daunting. It can seem overwhelming. It's very easy to get lost in the sauce. But each individual concept in and of themselves is simple. So this whole experience is just a long string of simple ideas. So what you have to do is give yourself time and work on this when you're fresh. Again, I do best when I first wake up. Like I be waking up at 2 in the morning, 3 in the morning, like every day, no alarm. And I'm up for hours. And so that's when I would study this stuff. And that's where my mind is the most clear. It's the least amount of distractions. There ain't nothing on TV, obviously with internet, so it's different this day and age. But most people are asleep. It's quiet, and I can just focus and just do it part by part, right, into small steps. Okay, we got a solid 10 minutes. So that was a fun adventure. Obviously, I'm going to have to leave this one as an exercise for you because we do need to kind of touch on the next section. I just want to kind of scan. I think that's it for this one. That was the culmination. And I think that's like the hardest part. Okay, so I'll make a copy of this available momentarily. Let me glance at the next section, 3.4. So far, Zoom seems like it's okay. I don't know why it booted us off. I'm going to have to reach out to tech to see, hey, do we still have a full version of Zoom? Let's see here. Are you behaving? Okay. View as a single page. Okay. So that was fun. Like I like that kind of stuff. I do my best to try to be clear, but I can acknowledge that sometimes it's a little bit rough around the edges. But I try to within a lot of time that we have, do the best that we can. Okay, so this section 3.4 is optimization. So finding absolute max and absolute min. So what this is, and I'll do my own summary. Finding absolute max and min is pretty much the same as finding the local max or min. The only difference is, in this case, we have endpoints. So we still do the first derivative test like before, but we also test the endpoints. So once we have it in a closed interval, we have some endpoints to test. Now we can talk about absolute max and min. Again, absolute max and min has to be on a closed interval, not an open interval. So a few objectives here: find the absolute extrema using max and min principle 1. Find absolute extrema using max and min principle 2. Suppose f is a function with a domain I. We say f of c is an absolute min if f of c is less than or equal to f of x for all x on the interval I. It should say something where I is a closed interval because you got to be able to test the endpoints. F of c is an absolute max if f of c is larger than all nearby y values for all x in that interval. So the extreme value theorem, a continuous function f defined over a closed interval a to b must have absolute max value and an absolute min value over that closed interval, right? So once we start exploring a closed interval, now we could talk about absolute max and min. If instead of square brackets, if those were parentheses, then the best we can do is talk about relative max or relative min. Okay. Okay. Suppose that a function is continuous over a closed interval. To find the absolute max, first find the derivative, then find your critical values. List the critical values along with the endpoints, and then evaluate the critical values with the endpoints. And then the absolute max is going to be the largest y value. Absolute min is going to be the smallest y value. Okay. So here in this example, pen. So finding the absolute max and min. So all we're going to do is first find the first derivative. So we're going to explore f prime of x. It's going to be what? 3x squared minus 3. Okay. We're going to find our critical values. Now we're finding the absolute max and min over this closed interval. Let's find our values of x that makes this either 0 or undefined. So we're going to set this to 0 and solve. We can factor out the 3. We're going to be left with x squared minus 1 equals 0. I think we get what? Plus or minus 1 as our critical values. Okay. So then what we need to do is basically do a test of values, like x versus f of x. Our endpoints, we have this -2. Here's our -1, 1, and 3/2. So what we did, in this table, we included the endpoints, which is the -2 and the 3/2, along with the critical values, our candidates for critical values that we found. We probably should do our first derivative test, but I'm just going to kind of go with this for the sake of time. So then we need to evaluate f with these values. Okay, I'm going to use my calculator. Right here. We got a solid 10 minutes, just shy of 10 minutes, right? More like 8 minutes, but we're going to go with this. Come on. You just love to make me load this file. Okay. Now I got to go find it. It's going to be here. What is this? Where is the home page? There it is. This one right here. Let's go. Let's go. Come on. You know you want to open today? Come on. I need this folder to open. Okay. One more. This is the page. Let's go. Let's go. You're eating into our precious time. Let's go. Let's go. Come on. You can do it. I believe in you. Let's go. Let's go. Oh, come on. It doesn't want to load. Calculator. Need my files. Man, we must be in some kind of retrograde or something. 10 minutes. Got the warning again. Here we go. Well, I mean, we're pretty much about to wrap up anyway, but I'm gonna have to reach out to them. I need this file to open to use my calculator. Oh, you know what? This is that Apple stuff where they intentionally start to slow down your device. That's exactly what it is. That's why it's behaving like this. I gotta see if I can find this another place. I might be able to pull it from my phone. I need to sue them because they've been sued for this before, for this very thing. Let me see if I go. Come on. That's the only reason it's behaving like this. Because it's, I only use it for work. Files. Yeah, this is them. Because on my phone it's working. I think it's this one. I want to copy this. Share. Copy. Copy link. I don't know if I got it. Let me try again. Copy. Share. We got 5 minutes. We're going to use it. Copy. Okay. Hopefully it'll allow me to paste. Hopefully the handoff. Oh, there it is. Look at God. Okay, whatever. I told you. Man, Apple, man, I got to sue them. Because again, they've been sued for this very thing. Because I know this is exactly what it is. They've been sued for this before, and I already knew. I just need to go ahead and do it. And I'm pretty sure they will settle. They will settle because it's the exact same thing, and they don't care. They got plenty of money. Like they don't care. They're gonna keep doing it. And then, just give me the money and we'll call it easy. Just give me enough to get a new device, and we'll be like, okay. Or just give me the new device. I'll take that too. Okay. Oh no. Hopefully we're still logged in. Okay, we got a solid 5 minutes. Okay, so let's. And I know that Zoom is gonna cut off on Zoom. So, okay, so let's go to our y equals. We got this x to the power of 3 minus 3x plus 2. Okay. All right, I want to evaluate this when x is negative 2. So when x is negative 2, we got 0. When x is negative 1, we get 4. When x is positive 1, we get 0. And when x is 3 over 2. Okay. Let me hit math here. Math is a fraction. 7 over 8. Okay. So the max. So then from there, we would say your absolute max is this guy because that's the highest y value. And then we have two absolute mins. It could be this one and this one. Okay, I'm just gonna wrap it up because we're out of time. Okay, so the derivative, it exists for all real numbers, plus or minus 1. Okay, so we got those values. Absolute max is 4. Oh, on that closed interval, when x is 1, so 1 comma 4 was the absolute max. 1 or negative 1? We got negative 1. 3 plus 2 is a 5. That's a negative 1. I think they made a typo. Yeah, they even got it there. Yeah, that's supposed to be a negative 1 right here. Let me make that correction. It's supposed to be a negative 1. The absolute minimum value is 0. The minimum value is y equals 0, which occurs when x is 2 and 1. Which we got both of those. Okay. All right, I'm gonna have to leave this as an exercise. So then max and min principle 2. Suppose that f is a function such that f prime exists. We say that f of c is the absolute maximum value if the second derivative is negative, and f of c is the absolute min if the second derivative is positive. If there's only one critical value on the closed interval, then we can use the second derivative test. So that's essentially an extension of that second derivative test applied to max or min. I just include the endpoints. All right. So we would need the second derivative test. I'm going to have to refer to my recording for that one. Use my recording. Same thing. I think for the rest of these, we might have to use the recording. So we did the best that we could for 3 and 4, for sections 3 and 4.